welcome to this Bioprocess International Ask the Expert webcast. I'm your host, Alex Nicolaitis, the webcast coordinator for Bioprocess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we'll begin the Q&A portion and I'll ask our speaker your questions. Your questions in the Q&A window will only be visible to myself and our speaker. So thank you for joining us this morning. It's now my pleasure to introduce our speaker, Michael Rauscher, Associate Principal Scientist, Process R&D Enabling Technologies from Merck.
Thank you, Alex, for the introduction. I'm excited to speak about some of the work that we've done today. So we'll be focusing on evaluation of a new multimodal anion exchange resin for an assortment of different biotherapeutic process challenges. So if we look at multimodal chromatography, it's provided a lot of value in the biotherapeutic space due to the ability to kind of provide selectivity for an assortment of different impurities. So if we look at a monoclonal antibody, there may be product-related impurities, high and low molecular weight species. There's also an assortment of process-related impurities, host cell proteins, DNA, from the expression system, the need to show viral clearance, deal with residual protein A ligand. And as we've seen, the space kind of veer towards more variation in protein therapeutics, it can provide even more value. If we look at multimodal resins, that have been available for some time, there's several. The space for anion exchange particularly, a couple of the offerings have been strong anion exchangers with hydrophobic character. So Nuvia wPrime 4A has quaternary amine, and then an aromatic group that gives kind of more hydrophobic selectivity. But the new resin that we evaluated and we'll be focusing on today is Nuvia wPrime 2A. So you can see ligand is quite similar to wPrime, with the difference that it's a weak anion exchanger with the ability to protonate there. And the pKa of the ligand itself in this case is 7.4. So as we kind of set about to do some evaluation, we really kind of looked for properties of the resin and which molecules it might make sense to apply it to. So if you look at the top left resin properties, again, wPrime 2A is a weak anion exchanger. So we see the pKa more down in that neutral range, whereas some other resins that we have experience with are all strong anion exchangers. So you see some multimodal towards the top there, where the hydrophobic surface area of the ligand is a bit higher. Towards the bottom, you see more traditional ion exchangers, where you're really just binding and separating based on charge. And then with protonation of the ligand on the bottom, you can see how the charge on wPrime 2A varies a bit in a space where we might be interested in operating, while wPrime ligand would be fully charged throughout that space. So then kind of piggybacking off of that, looking at properties of some different molecules in our pipeline that would be interesting. So the scatter plot shown here has determined isoelectric point on the x-axis, and then the y-axis is a normalized hydrophobic surface area, so a percentage. And what's kind of shown there is a variation of MABs and MAB-like molecules, but in this case, we kind of picked out three particular ones that were of interest. So going left to right, you see a bispecific antibody with relatively low PI around 6.8, an IgG4 just a little bit higher. And then as you move right kind of towards the center of the cluster, kind of a typical IgG1, relatively well-behaved, but I'll describe some of the process challenges on the next slide. So if we expand a little bit and then really focus for these kind of probing what we would look to improve in development. So bispecific kind of rough process comparison, polishing was being done with strong AX, strong CX. Challenges that we were interested in improving. We're seeing very low yield on that strong AX, a lot of product binding, and a mix of high and low molecular weight species that the two different steps we're dealing with. For the IgG4, there's a multimodal strong anion exchange step being run in flow-through mode. That step was really focusing on dealing with a couple different HCPs. So they're noted on the chart at the bottom as well. One that's in quite high abundance at the lower PI, and then an enzymatically active HCP at the upper end, up around 8.5. And then finally, the IgG1, again, relatively well behaved. We're comparing to just a protein A followed by strong AX in flow-through mode, but seeking more robust impurity clearance in that two-step process. And there is a notable amount of that high abundance HCP number 1 as well. So to kind of drill deeper on each of those 3 different molecules, we did some high-throughput screening to explore that design space. So this is plate-based with the wPrime2A resin packed into plates internally here at Merck. And then kind of step through a batch absorption process, where we would equilibrate the resin, incubate for a period of time on an orbital shaker, and then use vacuum filtration to recover, apply our sample, and proceed. And we have this automated on a liquid handler. So kind of initial experimental design for the batch absorption, we were interested in looking at partitioning of each of the 3 product molecules across a wide range of mobile phase conditions, because we expect that there could be interesting selectivity across a wide range. So in this case, we're doing a 60-minute incubation with the protein. And then after vacuum filtering, we can quantify the amount of protein that's remaining in the filtrate and back calculate to determine what's bound to the resin. Also worth noting here that we're loading at a low amount of protein on the resin, 5 grams per liter. So trying to avoid saturating, we're really just looking to identify binding and non-binding conditions, and not deal with any, like steric hindrance, like binding sites not being available. And then with that bound to unbound ratio, we get a sense of partitioning on the resin. And then kind of looking at those values, we could map a space across the wide range of conditions, identify potential binding regime where logarithmic transform of that partition coefficient is above 1, as well as kind of an intermediate region, and then a clear elution region. So if we look at the IgG1, the results that we see are a significant amount of binding all the way across the space. This is not unexpected for multimodal AX. There's a lot of conditions, where some level of interaction based on either charge or hydrophobicity could be occurring. But we really see, just in this kind of bottom left corner down around pH 5.5 and 6, at lower salt, we don't see so much binding. But everywhere else, it's interacting with the resin to some level. Given some of the, processes that we were comparing to and interested in improving, we then kind of proceeded to look at evaluating Nuvia wPrime2A in a flow-through mode. So again, used the plate screening approach, but just loaded a much higher amount of protein, up to 100 grams per liter in this case. And then we're looking to identify conditions where product binding is limited. So I'd mentioned that, a couple of the other anion exchangers were binding a significant amount of the product, but maybe there's room to bind less here. And then for this wide range screen, also looked at the ability to bind impurities more strongly, just with a focus on high molecular weight species here. So then if we look across all 3 molecules, again, looking at the 100 grams per liter yield, we're binding maybe 20 to 30 mg per mil of product across a lot of this space. So translating to kind of 70 to 80% yield, not excessive product binding to these resins. But then when we look at impurity data, high molecular weight species, we see pretty robust removal at a wide range of conditions. So for both the IgG1 and IgG4, at higher pH, higher salt, maybe see some aggregate breakthrough. But in a lot of cases, we're reducing pretty effectively to down below 0.5%, maybe like 0.6 to 0.7 for the bispecific. Even kind of focusing in on the center of that bispecific screening region, if we compare the size exclusion traces, We see reduction in the high molecular weight species, so about 1.6% coming in, reduced to 0.7, and then not quantified as much, but on the back end you can see there is some reduction in low molecular weight as well, kind of that shoulder and on the backside being reduced a little bit. It's just a little challenging to quantify on that assay. So we thought that was a pretty promising readout. From there, we really wanted to explore overall capabilities more thoroughly. So we used miniature columns on the liquid handler to characterize separation performance for additional impurities. So at this point, we used Nuvia wPrime 2A resin from a kind of scaled up manufacturing lot. And we're still looking to use high throughput based on what seemed like a promising wide operating space. Selection of the design points for this, are kind of scattered throughout there. So, there's potential to design more extensively, but we wanted a pretty random sampling, really only maybe avoiding that top right corner where aggregate removal for a couple hadn't been as promising. And then the miniature column setup itself, again, is on an automated liquid handler. We were using 600 microliter robo column, so 3 centimeter bed height. Compared to a lab scale column, we are scaling down by residence time. There is some difference in linear velocity then obviously, but within a regime where transport is behaving similarly, and then we're able to collect fractions for kind of extensive analysis. So I'll start to step through some of the case studies for IgG1. So this is a case where we're really just kind of looking for robust performance. And for yields, we see, pretty good behavior, especially at some of the lower pHs, lower salts that we screened. As we start to increase salt and get more into that hydrophobic range, get a little bit more binding. But kind of those lower salt, we're easily reaching 90, 95% yield as we increase loading. And then, for everything, we're really getting above 85. And if we look at impurity performance, some promising things here, definitely some ranging with different conditions. So this was a case where that one specific HCP, HCP number 1, was present at a fairly high level, 110 nanograms per mg. And for every fraction that we collected off of here, we were below level of detection. So very effective removal there. As far as bulk host cell protein, just kind of by a more general ELISA, we see removal at some conditions. You certainly see some spread in those results in that middle graph. So the orange dashed line is the amount of HCP coming into this step, and then each point on the line graph, reflects that specific fraction. So you can kind of consider it a percent breakthrough. And we see for those kind of low salt conditions, we see very effective removal, from thousands of ppm down to less than 100. Those higher salt conditions, not as good removal, maybe dependent on kind of the distribution of HCP that we're dealing with. And then we see pretty robust high molecular weight removal at all conditions, not a lot of sensitivity there. So kind of summing the IgG1 up in a couple notes, it does look like at low ionic strength, it could be a feasible replacement for a strong AX resin in a 2-column process. So if we compare some of those attributes, similar yields, similar overall HCP reduction, maybe a little bit of improvement in high molecular weight species clearance, and then a pretty good step in removing that one problematic HCP. And I think there would be some area for further development here if we were to screen further. I'm just kind of looking at higher pH and lower ionic strength. So we pushed up to pH 7. There's potential that we could go a little bit higher here given the PI of this mAb. And then it'll be a little bit of a recurring theme, but would be interested in assessing viral clearance. So next case study is the bispecific antibody. So this was, yield was down around 30% for strong anion exchanger at loading comparable to what we see here. And this has a little more product binding than we saw in the IgG1. but relatively high yields for these ranges screened here. So if we push loading up to around 200 grams per liter, getting an 80% yield. Then if we look at product quality, host cell protein, we're getting a pretty consistent about twofold reduction at all pHs above or equal to 6.5. So you can see a little bit more breakthrough for the pH 5.5 condition. Again, we don't see much change over time. So it does seem that there's a population that's not really cleared effectively based on properties here, but then a population that is cleared very effectively. And then for product-related impurities, this is like tracking percent breakthrough fraction by fraction, whereas the bar graphs like represent an actual pool at that point. So the fraction by fraction breakthrough, we can see there's low molecular weight species that are breaking through earlier than the product in that first fraction, and then it sort of levels out. High molecular weight species, there's a few different types that we're dealing with. So we see a little bit of enrichment in one species in that early fraction, then kind of a drop down where, a lot of the aggregate we're still binding while product is starting to flow through, but you start to see a little bit of a gradual breakthrough. So for the bispecific, I think there's some promising results here that we would be interested in, looking to investigate further. It does provide significant improvement in yield compared to the traditional strong anion exchanger. Looking at the readouts that we're getting, we would still kind of need that CX to deal with some of the impurities that can't be handled effectively here. But side by side, just for the AX step, similar product quality with some room to tune, and then the big step up in yield. And then finally, the last case study is the IgG4, and this is the one with two different challenging host cell protein problems. So we see, again, kind of reasonable medium yields across a relatively narrow loading range here. But then when we look at the HCP data, again, HCP number 1 is at a higher level, 340 ppm coming into this step, and all fractions reduced below LOQ. If we look at HCP number 2, in that case, we're not quantifying the actual species itself. We're looking for a particular type of enzymatic activity and quantifying that activity. But we see for a couple of the conditions, we're reducing below LOQ in all fractions. The third condition, we see a couple points with some activity, but still meaningful reduction from the input. And then we see quite robust clearance of high molecular weight species as well. So this is a case where there was a step that was already kind of targeted for that problematic HCP removal. And for each of those two species, we see like a pretty notable step up. And we're seeing a bit less binding on this resin. And kind of probing Nuvia wPrime2A further in this case, there'd be the ability to load higher and assess viral clearance. So in conclusion, we found that high throughput screening for this resin allowed us to kind of look in some different spaces for potential utility of the resin, and kind of explore multiple applications rather than just focusing on one case, and found that there could be some benefit with the varied charge on the ligand compared to some other resin options. And again, like through the 3 different case studies, saw robust performance for a potential 2-column process, less product binding for the bispecific, and then very effective clearance of 2 high-risk HCPs for the IgG4. And for more information on the Nuvia wPrime2A resin, or to request a sample, you can visit the link on the page there, biorad.com/wprime. And would like to acknowledge some of the other contributors. So Michael Hartman has done a lot of the homology modeling work that we kind of referenced when we were framing resin and protein properties and prioritizing some experiments to do here. And then I think a handful of process and analytical colleagues for feedback and some experimental support, and the process chromatography team from Bio-Rad as well. I'm happy to take any questions.
Okay, great. Thank you, Michael. And as a reminder to our audience, you can go ahead and type in your questions now. So our first question is, how are you identifying your problematic HCP species?
It's a good question. So initial identification used mass spec, either looking for abundance or like looking for something that would enrich based on a certain type of activity. When we get to the high throughput screening itself, it can depend on the species. So for kind of the HCP number 1 that I showed, there was a specific ELISA for that HCP. For HCP number 2, where we're using the activity assay, we'd use mass spec to kind of identify the one that was present, but then we were actually tracking activity and degradation of a surrogate to quantify there. So not like a direct ppm calculation.
And our next question is, what is your method for assessing the hydrophobicity of the molecules?
So Michael, who was co-author on the presentation here, determined or created some homology models using Mo software, and then kind of what was shown on the plots showing relative hydrophobicity. It's just using those homology models, looking at surface properties, kind of with a cutoff for the for an area that would represent a patch, and translating that to that percentage.
All right, well, it does look like we are running a bit short on time, so if you don't get to your questions, we'll be passing them along to Michael, who can follow up with you directly. So please go ahead and continue to type in any questions you have, and we'll get those passed along. The last question for the webcast is, were the 3 case studies performed at the same column scale across the control and Nuvia wPrime processes?
So that's a good question. Everything that we showed for Nuvia wPrime 2A here was done on RoboColumn. For the control processes, especially for the IgG4, there's a lot of kind of direct comparison at the same scale. The 2 other molecules, some of that data is from lab scale, but we have across a variety of MABs in particular, kind of good scale correlation between that miniature column and like a more traditional lab scale.
Actually, Michael, it looks like we do have maybe time for just one more question. If you do, is that all right?
Sure.
Great. So this last one will read, it seems the ligand charge across the pH range in wPrime gives you more workspace for your DOE than a strong AEX. Is that true?
Yeah, I think that's definitely fair to say, especially kind of looking at the PK of the ligand and a lot of the proteins that we're looking to purify and that are of interest. For multimodal DOE, like we're always kind of looking at balanced charge and hydrophobicity, but then you're getting more range in charge here. So.
Gotcha. Well, Michael, that is all the time we have today. So I want to thank you for your time.
Thank you, Alex. Thank you all.
Yeah, thank you to the audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website. And as a registered attendee, you'll receive a follow-up email providing you with the direct link. We look forward to having you join us at future Bioprocess International Ask the Expert webcasts. Look for those announcements in your inbox. Bye.
Thank you.